Assalamualaikum dear students. I would like to welcome you on the seventh lecture of numerical analysis and numerical methods offered in fall 2020. Uh, this is the first part of the lecture and we call it lecture 7A.
And today's topic is very interesting as well. And I must say it is not that difficult. And so far, we have not discussed so much difficult concepts as well. But this is one of the fundamental topic as well that we want to discuss here. So, idea, what is the idea of this topic and how do we discuss, how we'll handle it? I will cover now. Okay. So, student, this is how we have to deal with. Number one, the topic is called numerical. Although in a course contents, the title was mentioned as a numerical integration and differentiation, but basically we have to deal with numerical integration. Okay. Yes, it is the same integration that you are used to of it, but do not need to be worried. We are not going to use any analytical approach. We are not going to integrate by using U and P or any other. We have some smart strategies that can give us approximate answer rather than we have to solve some complicated problem. Okay, students. So let's have it because this is something new topic has nothing to do with operators and difference equations. I mean we are moving in some other dimensions now. So let me create some background about this topic, like what we are expecting from it. Let me tell you that this is the new topic and that topic needs to have in this topic we have to cover two aspects. One is the numerical integration, how do we numerically solve the integral problems, and obviously we also apply once we know the numerical integration. You all know that we can apply the technique to solve the differential equations as well, because in differential equation you need to numerically integrate, you have to integrate them, but here we will do some numerical techniques. Okay, so in this topic, that is numerical integration, we have to discuss two aspects. Number one, is that part we have to discuss is called integrations. Okay, obviously they are all numerical integration. You can divide it like that, and the other part that we have to discuss is solution of ordinary differential equation. Just not difference equation, is a differential equation. Okay. Okay, so this is the differential equation. So in this topic, it is a very vast topic, but for our course point of view, we just need to learn few methods, how they apply, and what are their instructions. Similarly, in this heading, we also have to discuss two or three methods that we have to apply for the solution of ordinary differential equation, and most of the ordinary differential equation in our case is first order. Okay. Now, also the method we are going to discuss may be used to extend to higher order, second order differential equation, but our prime focus for this course is towards the first order. So these are the two topics in lecture number 6 that we'll try to cover. I mean, it will start from today. Maybe I need lecture number 7 as well to cover these two things. Okay, so that's the main uh, uh, point. That is, you should know if I'm talking on numerical integration means that what are the topics included in this topic. So one is simple integration. I think I should write it down like that. Integration of function f of x. Okay, integrate करना. We have to integrate those functions like f of x and a numerical solution of differential equation, usually first order. Okay, but whatever concept we will discuss, we will extend. But the common point in those in the all of these strategies that we will try to get approximate answer. Okay, we will try to get approximate answer. Also, our logic is like that. If we can do some extra effort, then we can make it very close to exact. But always, whatever the accuracy you want to impose, we get approximate answer. Okay, but they are very good resembles to the exact answer. Approximate answer. Now, when we are saying approximate answer, it is quite clear to you. I have used this strategy many times. This means that I want to compute numerical approximation. Okay, numerical methods or numerical techniques. Keep in mind this thing. Okay, the one thing that I forgot to point out, the course outline that I shared with you, it has a heading of this topic is numerical integration and differentiation. I am not adding the differentiation here because differentiation we have some sort of already discussed in the form of operators. If you remember, you have to compute dt over small t or dx over dt from a data set. So this is basically covered in that aspect. Okay, so this topic in the course content will be having heading as numerical integration and differentiation, but I am calling it as a numerical integration because the only topic that we have is related to the numerical integration. We have to perform integration. So we have two branches. I will start from this side to integrate a normal function based on certain methods. Technically we have to discuss only three methods here in this heading, and roughly three methods there. So total six methods we have to discuss under this topic to cover this topic completely. Okay, so three methods for integration only and three methods for solving first order differential equation. It is not difference equation anymore, it is differential equation. Okay, continuous variable or discrete. I hope you know the difference between these two. Approximate answers. Okay, and the strategy is based on numerical methods or numerical solutions. Okay, so let's move then. As I told you, I will start from this part. So let's discuss that concepts of numerical integration and what was the reason behind it. That to discuss this topic and how do we do that? What's the theme of this? Because you will notice that if you understand the theme correctly, rest is just a repetition based on the accuracy of a same thing. What does this mean? You will understand now today. Okay, so let's move towards that application just towards this topic. Okay, so here from numerical integration I am discussing basically the numerical integration of a function part. Okay, numerical integration. I know that maybe students of some of them are confusing, sir. If this is numerical integration mentioned there, why you put this numerical integration up of it? Student, numerical integration is a general technique, which is this part only. But this technique of integration would be applied on the differential equation solution as well. If you remember, if I ask you to solve a differential equation, so you need to do one thing. You have to integrate it. Okay, so when you have to integrate means you are solving analytically by integration. However, we do not want to do the exact integration here, so we have to do something called numerically. So this means that we are using a concept of numerical integration that we learned in this course and applying it to certain extent on the solution of the differential equations as well. So that's why I divided into two branches. Okay, although in a course content you will find it they are just written together. So mainly that's a big difference between these two. Okay, so there are few methods that we have to learn and then we have to apply to solve it on a differential equation, because to solve differential equation means that we have to integrate it. That's why numerical. So I'm just calling it again numerical integration, which means that I want to discuss numerical integration of a function f of x. कोई भी there is a function. What does this means that? This means that I want to discuss a numerical solution of a single variable function. I mean to say, for example, if I ask you to compute this integral, this is the integral symbol a to b f of x dx. This symbolization I will use many times in this working. So f of x equal to this one. So you all know this is called definite integral. Definite integral as it has the limits. Okay, definite integral a to b, and whatever be the answer is basically, you all know that from your preliminary analysis, that whatever be the answer I will get, we will get it my, let's say if I integrate this function, there is an integral of this function uh, is f of x. So I can say f of b minus f of a would be this, where capital F of a is the integral of this function. We are not solving it, so we are not interested. But let's say whenever we get the integral, we have to minus upper limit minus lower limit, if you remember that part. So whenever you solve it, you get some number, some answer. Okay, so there is no constant of integration because this is a definite integral. which means that you will get a finite answer. Okay, there is no ambiguity in your answer. So geometrically, what does this mean? If I plot this f of x, this is usually called integrand, if you remember. So I will use to call it integrand a lot. So integrand means the function that you want to integrate, and this a and b are used to call, if you remember, they are called limits. Upper limit is b and lower limit is a. Upper limit and lower limit. We used to call it, we want to integrate it from a to b, which is lower limit to upper limit. So if I integrate, I will get some integrand, which is not a part of this code because we are not going to do anything analytically. But let's say if we integrate, then we will have to subtract upper limit and minus lower limit. So we will get some numerical answer. For example, 4, 2.9 or something. What that number represents, that's the point. So in graphically, geometrically, we all know that if I plot a to b, okay, a to b, then the graph of that function is represented. For example, the graph of this integrand will be represented like this one. Just a rough example. So y equal to f of x is there. So this part is here and this part is here. Okay, so I know that this is the lower limit and this is the upper limit, as this is x, this is y, and this is the graph of. So whatever be the answer I got by subtracting upper and lower limit correctly means that that number represents something. And we know from the our preliminary knowledge of the calculus at undergrad level is that this represents the area under this curve. For example, let me write down if the answer is capital C here, for example. This C has nothing to do with the constant of integration. Okay, do not mix it. I have used AB there, so I'm calling it C. If whatever the answer you get is C, so that C, in fact, rather than using a C, use it like that. Whatever the answer is capital A, this is area. So whatever the numerical value we have A, by integrating exactly, is basically represent this area. Area means the area under this curve and above the x-axis. So this is represented analytically if you solve it. Okay, we all know that one. Okay, so I just give you a brief recap. We are not going to use partial fraction, we are not going to use by parts, or we are not doing substitution. We do not have to do all these things because these all things are designed for analytical purpose when you can solve the integral exactly. What we want to develop a knowledge is that there are many integrals that we cannot solve analytically, or we can solve it but they are very time consuming. For example, just for recall, it is still a background. I have not started those methods that we have to discuss under this heading. Because student, if you don't know the background of the study, it is useless then. You just know that just you do the practice. So first you have to understand why we are doing this. Like what's the reason behind it? If our calculator can give the answer or we can solve it or we have learned it, why this is again repeating in front of us. Okay. So for example, if I ask you to solve a simple integral square e raised to the power x and integrate it to certain point. Okay, let's say we do not want to solve exactly, but let's say there is some point a to b and dx with respect to dx. If you want to integrate, you all know, sir, we have to apply by parts. And according to the by part, we have to suppose this as a function equal to some variable whose derivative needs to be computed, and this needs to be integrate, and then we have to do it something. If you remember, if you remember that if you solve this part, so you will have some situation. Maybe I'm writing something like that. Ex minus integral again of ex, if you remember. Okay, or something like this. You can verify it. For example, this is the answer. The point that I want to establish here is that it has a degree 2, so you need to integrate it 2 times. First time you integrate, by applying a by part, you will get this formulation, and now you have to integrate it again. So imagine that, for example, there is no power 2. In fact, the power is uh, 100, for example, and I ask you to solve it. So if you want to solve it, you are 110% sure that, sir, we have to apply a by part there. So once you apply a by part first time, so you will get something like that: x 100, x 100, or x 99. You can see the main point is that minus integral x 99 e raised to the power x dx. Then to solve it again, you have to apply by part again in this region. When you apply by part again here, when you apply a by part again here, so as soon as you apply the by part again here, then you will get then you will get another relation which is something like that: x 99 ex minus integral x 98 ex, and so on. This will continue. So you, and then you have to apply by part again. So you know the method, but the integral is very lengthy in this case. So solving it analytically will take time. So is there any way that we can solve it? Obviously, you can solve it using calculator. But question is that if it is taking so much long time, then how the calculator can solve it in just a minute? It is not just because of the efficiency. Process is same. And the reason is calculator does not work on these analytical techniques that you have learned. They work on the numerical techniques. Numerical techniques that we are going to learn in this topic. Similarly, there are many other integrals which are very difficult to solve as well. For example, e raised to the power tangent something of tangent inverse of something or sine. So they are very complicated to solve it. So when they are so much complicated that you have to integrate, rather than using an analytical technique, we try to apply a numerical technique, because numerical technique does not follow the conventional way of handling the numerical integration. Okay, so I hope that the background is enough for this part, that there are two reasons to discuss numerical integration. One, sometimes we know the method that how to solve it. For example, here we know that this could be solved by using by parts, yes, that is two functions are multiplying, but the length of the question is too long. Sometimes the integrand, that is the function that you want to integrate, for example here, is so complicated I don't know how to find the integral of that. So we will try to switch to a method that can gives us answer, because this is definite answer, definite integral. We will get a some number at the end like this one for sure. But if we cannot find the exact answer a, so can we do something to get a approximate of a, like close to a? So this is the main theme of this topic. Like, okay, if we cannot solve any integrand, or integral to problem directly or analytically with exact answer, is there any way that we can solve it to get a some numerically approximate answer, like close to that answer? For example, close to, what does close to means here? That's I am repeating it many times. For example, the exact answer is two. Exact answer is two. So it does not means that approximate answer means 2000 or minus 200. No, approximate means it has to be very close to 2 as well. Like for example, it may be a 2.0001 or something, or 1.999 something. So it is not 2. So this is not exact, but they are very close to this answer. So we will try to figure out some other alternate method that can give something like this answer. If the exact answer is 2, can we generate something close to that? Then it is fair enough. As far as engineering application are concerned, we are not dealing with the exact uh, method like mathematicians do, but for engineering application problems, and if you have to solve some integral and which is very difficult to solve, or we can do it using calculator. But whatever the calculator is telling us, it's based on some numerical strategy. So in this course you will learn as well what are those methods that can solve this part, and what is the strategy that can generate a solution numerically. So student, this is just a rough slide which I made it for you to, for a brainstorming or just to understand the topic that we are discussing today. Okay, so in the theme of this, let's start, and I hope that this method is to certain extent at calculus level you all are familiar. We have to discuss only three methods here. The first method that we have to discuss for numerical integration is called trapezoidal rule. I'm quite sure you have gone through to certain extent to this method in in calculus class or some other courses, but uh, it's called trapezoidal rule. Okay, trapezoidal rule of integration. Although this is for sure it is for integration, but let's point out complete heading: trapezoidal rule of integration for f of x. That's interesting. I'm whenever I'm writing f of x means I want to point out that I want to solve a problem that is based on single variable. Okay, single variable, because these are also the functions that equal to f of x y. It become multivariate function. So we can apply trapezoidal rule there as well. But what we are discussing here is only for first single variable function. Okay, so sometimes I will just root trapezoidal rule, but the complete heading is trapezoidal rule of integration for f of x, like single variable function. Okay, so what's the theme behind it? It's a very interesting theme. Okay, so theme is the problem that you and whenever I try to explain a problem method to you, always assume that there is some function f of x which you want to integrate from A to B. Okay, this is given to you. This is always given to you. Okay, and you want, if you want to apply any method, let's say you want to solve an integrand which is definite in nature, that is, you know the limit from A to B. But the problem is that this f of x has two issues. Maybe the process is very difficult, lengthy, or you don't know how to integrate this function. Also, you know that wherever you want to solve this integral makes sense, and if you know the answer, then you can continue further your research work. Now, question is how to solve it. Wait. So we choose to solve it approximately. Okay. So the theme is, this is the key point and the theme, which I will explain in trapezoidal rule, but it will be hold for all other methods as well. That is two more methods with little bit modification. So the theme that you have to understand is that, okay, this integrand is very difficult to solve. Assume that throughout the time. Whenever we are discussing, means assume that it is very difficult to solve. So we were switching towards some numerical technique and we choose trapezoidal rule. Trapezoidal rule or trapezoidal technique. How we will apply this strategy? So strategy is quite simple and very simple. Idea is, this is your integrand. I will explain it in an analytical part, like mathematically as well and geometrically as well, so that you have a clear vision what does this mean. For example, this function is difficult to solve. So theme is, if this integrand is difficult to solve, okay, we know that, is it possible, to replace this integrand f of x, replace this integrand by some polynomial of suitable degree? That's the interesting part. Why? For example, you have an integrand, very complicated integral, okay? Very complicated. But what you want to do, you want to replace that integrand by a polynomial of suitable degree, the degree of the polynomial that you know. Okay? Why? Because student, you all know that the polynomials functions are very easy to integrate. For example, if I ask you, you have to integrate 2x square plus 3x plus 4. So most of you can do by heart as well, because this is a polynomial of degree 2. So you can replace it. So whatever written here, this could be written like that as well. Polynomial of degree 2 dx. Okay. So, and let's say it is a to b as well. So this is also a to, so this is also a to b. Clear? So that is what I want to say. So whenever I say polynomial of degree 2, which means that this has the highest degree 2. So here what I'm saying, that rather than solving a integrand which is very difficult, is there any way that we can replace our integrand by a polynomial of suitable degree? This is the main theme of the numerical integration. Okay. Now question is, what we exactly do in trapezoidal and how? So an idea is, in trapezoidal, I said you have to replace it with the suitable degree. This is the degree of the polynomial. And what does degree mean? Degree means the highest power of the polynomial. Here I have explicitly write certain polynomial, but in general it could be any polynomial, like in general. So what we do, this is the just a background. So main point is here. So what? So this is the theme. Is it possible that we can replace f of x into pnx? Rather than writing further here, I will try to explain this thing geometrically to you. For example, student, this is the graph of the integrand. That is the function that I want to integrate from a to b. If I want to integrate it from a to b, then this would be my function f of x. Okay. So let's say it is very difficult to integrate, but I can plot it. If I try to plot it, then what I need few, let's say, line. Okay, so like integrand is plotted here. Let me explain you to those who are still confused. For example, if I ask you to plot a to integrate, let's say, x e tangent x dx. So it may be a difficult, or someone can do it easily, but let's say it is difficult. So this is whole thing is our f of x, small f of x. If this is f of x, can I, okay, it is difficult to integrate, but can I plot it like that? For example, if y equal to x e 10x given to me, can I plot it? Yes, we can do it. We will select different values from a to b, and we will put different values there, and we get some points, and then we will sketch the graph accordingly. So integration is difficult, but we can plot its graph. Or maybe using a computer, we can plot its graph. So let's assume that I have plotted that integral, which is very difficult to solve, and the graph is look like this one. It is rough graph. Obviously, it is dummy graph, but let's say this look like some function. So technically, so it starts from there and end this straight line is end there. Okay. So this is the starting and this is the ending. So technically, I want to find the area under this curve, but we cannot solve it because integrand is difficult to handle, but we can plot that graph. So once we have this graph idea, what I'm talking about, this is the graph of f of x. Okay, but what I want to do, I want to replace it. So let's say using black color, I want to highlight one thing. What I did, I said rather than integrating this f of x, which is very difficult to solve, let's replace that integrand by another function. So what I did, let's say I replace that integrand by a straight line. And obviously we all know that whenever we are dealing with a straight line, this means that this is a polynomial of degree 1. We all know that a straight line is a polynomial of degree 1. For example, you can replace it degree 2 as well, degree 3 as well, degree 5 as well. But just for basic understanding, let's assume that the main integrand is this one, which we have to solve white color, but I replace it with a straight line with the condition that if the answer is f of x is at a is f of a, then this will also generate a f of a, and if the answer at this white curve is f of b, then this will also generate the polynomial is f of b. So in other words, it is matching the endpoints. You can see that endpoints are matched. So whatever be the answer I will get from the white curve, I will get the same answer from this black curve as well at the following points. Okay, so this black line is represented by a polynomial of degree 1, and this white line is represented, white curve is a exact function that is we want to integrate. But why I replace it with a straight line? For example, so in a straight line, if I replace it, then I can see that if I try to compute the area under this curve of a white curve is very difficult because we cannot do that. But what I can do, I can compute this area of a black line under this black line very easy, because if you look carefully, this is like a trapezoid. Look carefully, this is like a trapezoid. You remember the definition of trapezoid? Trapezoid says two sides are parallel. I have not drawn it properly, but they are parallel sides. Rectangular Cartesian system, so it is parallel, and two sides are not parallel. So if I claim that my integrand f of x can be replaced by a polynomial of degree 1, although it look like it's not a reasonable argument here, because if I compute the area under this black curve, let me shade it for you. Only this part, this area under this curve, then you can clearly see that okay, this is could be an approximation, but that does not give the exact answer. Why? Because I cannot compute area outside this line, because I want to compute area under this black line and this, and whatever the answer I am getting here, I am trying to approximate as an integral of this function, which is wrong, because I assume that this f of x, this white curve would be replaced by this one. What does mean? Means that rather than reading f of x anymore, I will read polynomial of degree 1, this black line. So if I ask you what is the answer of the white curve at this point, so rather than putting this in a white curve, I will put it in a black curve. Okay, so one can clearly see when I do this thing. For example, there is one point C. and I want to know what is the answer. So rather than putting it in this function, I will put it on this black line. So one can clearly see I am making an error in the computation. An error is with this amount of error. I am getting this answer. This is steric one, but correct answer is to be have a value from there to there. This is the height. So if I try to note f of c, then I'm not using the integrand, I'm using the polynomial. So I will try to put this value in a polynomial of degree 1, and whatever the answer I will get represent this function. So whenever I say can we replace our integrand by a polynomial of 50 degrees, means that we replace it with this some polynomial function which is very known to us, which is very easy to us. So here it does not matter how much complicated the white function is, you have replaced it with the straight line. Although this is not looking good because this is representing some error. So what are the errors are here? So if I say that this all black shaded region is the exact answer, it is wrong, because you can say that sir this part is not included, because you are computing only the area beneath this black line. So this white shaded area is not included. Let me shade it for you. This part is not included. This part is not included. Similarly, this part is I'm shading, making it shade in different style. This part is included, which shouldn't be, because this exact, if I want to compute the exact answer must be give the area beneath this white curve, not above this curve. So what I'm making here, I'm making a mistake. What I'm making a mistake is that I am not counting this area correctly. So if I focus only on this portion, I am only getting the area beneath this line, not this white portion is included. So we are making an error, and that error we call undershoot. What we call it? We call it, this is an error representation, and it is called undershoot. Means that you are counting something which is not exact. For example, the correct reading is 10, and somehow you are finding it 8. So this means you are underrepresenting the value. So it is called undershoot. And similarly, if you focus on this part of the error, you can clearly see that there is a mistake in it. You are counting extra. Technically, the area should be beneath this white line only. But you are counting this as well, because you are noting the area beneath the black line, which means that you are overshooting. Overshooting or over predicting, sometimes the word is used. Okay, so error could be undershoot and overshoot. So you are counting what is happening here. If the correct area is 8, then somehow due to the black line you are counting it 9 or something. So you are counting more than what is actually is. So idea is, can we replace our integrand by a polynomial of suitable degree? So whenever we say suitable degrees, means that we want to approximate our integrand in such a way by a polynomial that it will generate minimum error. The error should be minimum. If this is the reasonable approximation, then it is good to replace it. Why? Because this is very simple to find the area. I do not need to integrate this function. For example, if this integrand is replaced by a polynomial of degree 1, I do not need to integrate. I can easily find the area of this black trapezoid. Very easy. Sum of parallel sides multiplied by separation between them. This could be done very easily. So we do not need to integrate. But the problem is that, is it is it a good choice or not? That's the main point. Okay, this is we have to consider. But here I am just explaining you the theme of this topic. The theme of this topic is that replace your integrand by a polynomial of suitable degree. Okay, so this was the main purpose. Okay, so this was the main reason behind. This is the main theme. The theme, what's the theme is, replace your integrand by a polynomial of suitable degree, and rather than solving rather than integrating your function, integrate that polynomial, which is very easy, because polynomial just look like this one, and it is always very easy to integrate. So now I can write it down for you. So here what I say, f of x a to b, but we will not integrate f of x. In fact, we will integrate a polynomial of suitable degree dx from same region A to B. So whatever the answer that we are expecting from integrating f of x, we will not do that. We will integrate something which is equivalent of f of x, not exactly same, because we can see that it is giving the error. If it is exactly same, then there is no error. For example, imagine that this white line is exactly coinciding with this black line, so there is no error. In this case, logic is saying yes, this is possible that we will get no error, but in usually this is not happening. Okay, so ax pnx, and this is the example. So whenever we get this answer, this contains some amount of error. That's why I'm not saying exactly equal to. Okay, but if I want to put equal to here sign, then I have to put this quantity plus some error. I have to write down that plus some error. So this is the main theme. Although I'm explaining this theme based on under the heading of trapezoidal rule, but keep in mind that this whole idea will hold for all other methods as well. Okay, now in the next slide I'm explaining you heading is trapezoidal rule, but I am explaining you that what exactly we have to do in a trapezoid. In trapezoid rule, you can understand already because in trapezoid rule, I already used this word in the last slide. In trapezoid rule, we replace our integrand by a polynomial of degree 1. That's interesting. I told you we will replace with a suitable degree in trapezoidal rule. But here we will replace it. If you say that I want to solve it using trapezoid rule, so there is a fixed thing. Fixed thing is that you are replacing your integrand. That is, this is what you have to solve, and you cannot solve it due to certain reason. Exactly. So you want to solve numerically. So what you do, you will replace your integrand by a polynomial of degree 1. This is, you have to make sure that memorize it. I am not writing any degree here. Whenever we are talking about trapezoidal rule, we replace it with degree 1 polynomial. And degree 1 polynomial is quite simple. Degree 1 polynomial is represented like, for example, ax. Oh, sorry, we are using a b here. So let's call it a1, ax, and a naught polynomial. For example, 2x plus 3, 4x minus 9. It could be any polynomial. But how do we exactly compute that polynomial? That's a different thing. But keep in mind that the theme is, if you are saying I want to solve this integral numerically using trapezoid rule, so underlying idea is you are approximating your integrand. I have to write down this thing as well. You are approximating your integrand by a polynomial of degree 1. You are saying that our integrand can behave like a polynomial of degree 1. And we all know that polynomial of degree 1 means a straight line, geometrically. A straight line. Degree 1 is usually a straight line. If you plot it, you will get a straight line. Okay, so this is the approximation. That's why I use approximate. If f of x is just like a straight line function, also then we do not need numerical integration, we can solve it directly. But let's say in this case, then p1 and f of x are same, so there is no error in that part. But here we have some error, that's why I am using approximation. In the next part, we will also discuss how we can minimize the error, but this is the main theme. And geometrically, I can redraw for you. This is specific to the trapezoidal rule. Okay, so whatever the integrand is given to us, a to b, whatever the integrand is given to us, y equal to f of x, it will be replaced by a polynomial of a degree 1, and degree 1 means straight line. So here I am representing it with dots. Okay, so straight line dots. So now if I want to compute the area, I can compute, but I will compute the area beneath this dotted curve and this line. Okay, so this dotted curve is polynomial of degree 1. So it is just like the old example, but it is down. So if I want to compute the area, I will not compute the area under this curve. I will compute the area beneath this curve.